So let's take a look at an example using the range rule of thumb, how we would employ that. And I've downloaded some earthquake data that's part of the data set from the book. Let me see if I, yeah, this is the wrong one. No, where did it go? Yeah, all right, here it is. So I've got this data. There's two columns of data. One represents the depth and the other one represents the magnitude. So the first one, I think, is the depth of our data set. But if we wanted to employ the range rule of thumb, first thing we need to do is find the range. So I don't think there's an easy calculation for, or a quick calculation for range. You can't just type in range, but what you can do is type in the maximum of our data set, and I've given this one a name of magnitude minus the minimum, again, of magnitude. So the max minus, it doesn't like that. Maybe let's try it one more time. Max of, maybe it's because I'm not capitalizing it correctly. Max, let's just do it old school, of this data set minus the min. It should work. Mag. Still not liking it. What's wrong? Hate when this happens. Last try. You know what? We're going to do a real brute force approach. I'm just going to sort this, and we'll give it the eyeball test. So, sort it. Edit. Data. Sort from lowest to highest. So from 0 all the way up to 2.295. So that would be our range. The highest minus the lowest. So the range is 2.95. And back here. So the range in this case is 2.95 divided by 4. This is going to be a little bit less than 0.75. 2.95 divided by 4. 0.7375 for our estimate of the standard deviation. Let's see how that actually compares to the true value if you actually calculate it from our data set. So let me swing back over here real quick and type in standard deviation. So equals stdev of this column. And let's see how ours compares to the actual value. There. So 0.5873. So, I mean, not good, but not bad either. It's just kind of somewhere in between. But sometimes it's all you got is a little bit of the data, and you need to estimate things. So the true value, S was equal to 0.5, what was it, 85? Didn't get that, 5873. So like I said, not bad, but not great either. Now the number of standard deviations can help you mark something as being typical or atypical. And with that, let me introduce something called Chebychev's rule. So I think we'll hold off on Chebychev's rule to the next section. Well, no, it's on page 104, so we can do it. We can do it here. Chebychev's rule and the empirical rule talk about how much data you'll find within a certain standard deviation of the mean. So within k standard deviations of the mean, there will be at least 1 minus 1 over k times 100%, the k should be squared, times 100%. That portion of the data should be within k standard deviations of the mean. So let's do kind of a quick example here. Example. If k equals 2, then we get 1 minus 1 over 2 squared times 100% is going to be 1 minus 1/4 times 100%. 3/4 times 100% gives you 75%. So 75%, at least 75% of your data should be within 2 standard deviations of the mean in any data set. No matter how crazy it looks, you're guaranteed that at least that much will be within 2 standard deviations of the mean. Oftentimes, you can make even a stronger statement. Depends on whether or not you have a bell-shaped distribution. If you have a bell-shaped distribution, then things improve. Within 2 standard deviations of the mean, in a bell-shaped distribution, you'll find 95% of your data. In fact, within 1 standard deviation, you'll find 67% of your data, 68% of your data. If you go all the way out to 3 standard deviations of the mean, you've got almost all of your data. 99.7% of your data should lie within 3 standard deviations of the mean. So if your test score is 3 standard deviations above the mean, that puts you in rare error. That's pretty unusual to be that far away from the mean in a normally shaped curve. Let's look at problem number 18. It says, according to the freshman 15 legend, college freshmen gained 15 pounds or 6.8 kilograms during their freshman year. Listed below are the amounts of weight change in kilograms for a simple random sample of freshmen included in a study. Positive values correspond to students who gain weight. Negative values correspond to students who lost weight. Is a weight gain of 15 pounds or 6.8 kilograms unusual? Why or why not? Does that support the legend of the freshman 15? Well, let's find out a couple things about our data by entering it into a spreadsheet. You could also enter it into your calculator if you wanted to do that. Let me go back to our spreadsheets. Let's clear out this data here. In fact, I'll just cheat. I'll just do a new spreadsheet. And let's type in the data. So 11, 3, 0, negative 2, 3, negative 2 again, negative 2 again, 5, negative 2 seems to be really popular, 7, 2, 4, 1, 8, 1, 0, negative 5, and 2. There's 2 things that I want here. I want to know the standard deviation and I want to know the mean. So let's find out the mean first. Average. So the average of our data set here is 1.88. And let's find out the standard deviation. Standard deviation is 4.06. 4.06 about. So X bar is 1.888 and S is approximately 4.06. Now this gives us an idea of what's typical in terms of weight loss. Now keep in mind that this is in units of kilograms. So rather than always work on Google Sheets, maybe I'll switch over and do it on a calculator just to mix things up a little bit for you. We want to know what's typical. What's typical is this range. It's going to be x minus, or x bar minus 2 times the standard deviation to x bar plus 2 times the standard deviation. So let's calculate that range. So it's going to be 1.88 minus 2 times 4.06. Oops. 2 times 4.06. So that's going to be the lower end of what's typical. Negative 6.24. If I want the upper range, I got to repeat that calculation. So I'll just go back and do that. And the upper range is 10. So from negative 6.24 to 10. What's that say about this legend, the freshman 15? Keep in mind that 15 pounds is about, what, 6.8 kilograms? Yeah, 6.8. Would a 15-pound weight gain be atypical? No. 15 pounds, basically 6.8 kilograms is within that range. So 15-pound or 6.8 kilogram weight change is not atypical. It can happen. Now there's a lot of variability in our data set. It seemed like 15 pounds would be a little bit high, but it's not completely unusual. If you're curious to see that calculation on Google Sheets, you can do that pretty easily. Again, you don't want to have to type in these values themselves. What you could do is take equals and this minus 2, and then the asterisk above the 8 for your times. Minus 2 times that gives you your lower limits. And then I want to do the same thing for the upper limit, equals, and then this plus 2 asterisk 2 times standard deviation. So there would be your typical range. And the 6.8 that represents 15 pounds is in that range. All right. Is there any comments or thoughts on this one? Okay. Problem number 18. Now, we did spend a little time finding the mean from frequency data. I'm not going to try and make us grind out that calculation for the standard deviation from frequency data. You can get it. It's kind of an involved calculation. Let me show you that in the book. Oops, not there. How about here? It's this formula. So, like I said, it's an involved calculation. It's not something that would be very difficult at all with a spreadsheet, but it's just something that I'm not going to hold you responsible for. Instead, what I'd like you to do is try some homework. Try problems 1 through 21 and problem 37. Yeah, please. Mm-hmm. No, I thought the data here was in kilograms. These are in kilograms. That was in kilograms. Yeah, I see what you're saying. If it was the other way around, then it wouldn't make sense. Yeah. No, I appreciate that. So, yeah, so this is for 3.3, section 3.3, homework, try 1 through 21 and 37.